In this section, 11.2, noting that we are skipping chapter 11, section 1 in the textbook, in this section we're going to be talking about polar coordinates. So we're actually not going to be doing any calculus whatsoever, nor are we going to do anything that is brand new to you. The entire section is all review from your trig course. So of course unit circle is a big part of trig, and that will be a big part of this section, but again, entirely review. So hopefully you have some memory of doing this, and it comes back to you even more as I review some of the basic ideas. So in terms of polar coordinates, what we're doing here is where instead of using a rectangular grid to plot points by moving either vertically or horizontally in the x or y direction, we're going to be looking at r theta, where r represents a radius and theta represents an angle. So if we're plotting a point in a polar grid, what we're going to see are all of these concentric circles centered around the origin. Not drawn very well by me, of course, but we're going to start with our initial side of our angle here on the positive side of the x-axis, and then we're going to create an angle theta with the terminal side, and then according to the radius, we're just going to count out that number of circles in order to plot a point. Okay. So again, polar coordinates are expressed in the form r comma theta. And so one of the things that we're going to be asked to do is convert back and forth between rectangular coordinates or Cartesian coordinates and polar coordinates. So we know that rectangular coordinates, or again Cartesian as they're often called, are in the form x comma y, whereas polar are in the form r comma theta. So we need some relationship between x, y, r, and theta in order to make those conversions happen. So here are the basic conversion formulas. So first of all, r is the square root of x squared plus y squared. Or we can think of it as r squared equals x squared plus y squared. Theta is the inverse tangent of y over x. Theta is the inverse tangent of y over x. And then x equals r times the cosine of theta, and y equals r times the sine of theta. So hopefully you remember some of those formulas. Let's go ahead and use them in some examples when we are converting between polar coordinates and rectangular coordinates. So my first example, I'm going to be given 3 comma negative pi over 6, and what I want to do is convert it to rectangular form. So because this is currently in polar form, I can assume that the r equals 3 and that the theta is negative pi over 6. And I'm going to go ahead and bring in a polar grid right now and actually plot that point before we do the conversion. And in Canvas, I've made available a document that has a whole set of polar grids, so you can practice plotting points yourself as well. So again, radius is 3, theta equals negative pi over 6. So if you think about your unit circle, this is the angle 0, this is the angle pi over 6, here's pi over 4, pi over 3, pi over 2, and again I could go all the way around the circle. I want the angle negative pi over 6, so that's going to bring me down here to this particular line. And so I'm creating an angle with the positive x-axis and with negative pi over 6. So that creates the angle, but to actually plot the point, what I want to do is I want to go to that terminal side of the angle and I want to go out 3 radius lengths or 3 circles to plot my point. So that would be the location of the point 3, negative pi over 6. It's in the 4th quadrant of the polar grid. So let's go ahead and convert it to rectangular form, and then next to it I'll go ahead and plot that point in rectangular form, and we'll make sure that's in roughly the same location. So the actual conversion piece, I need to again take this point that's in that's in r theta form, and I need to convert it to xy form. So how do I get x when I know r and when I know theta? Well, x is always equal to r times the cosine of theta. And then y is always equal to r times the sine of theta. So all I need to do is plug in the r and the theta that I'm given in this point in order to get my x. So x is going to equal 3 times the cosine of negative pi over 6, whereas y will be 3 times the sine of that angle. Now you have to reference your unit circle knowledge to figure out what the cosine and sine values are of negative pi over 6. And we should get that x equals 3 times the square root of 3 over 2, because that is the cosine of negative pi over 6. And then y equals 3 times negative 1/2, because that's the sine of negative pi over 6. So if I finish this off, my rectangular coordinate that would correspond to this polar coordinate would be 3 root 3 over 2, negative 1/2. And again, I just want to plot that on my rectangular grid to make sure that it is in the 4th quadrant. Just looking at the signs, we can verify that, but roughly in the same location as when we plotted the polar coordinate. So in order to plot this 3 root 3 over 2, I'm probably going to want to approximate it. And so 3 root 3 over 2, if I use my calculator and type that in, that's going to be approximately 2.6. And then of course, let's see, I had negative 1/2 here. It should have been negative 3/2. Let me just notice that. Because the sine of negative pi over 6 is negative 1/2, and then of course multiply it by the radius of 3. So that should have been 3 times negative 1/2, which is negative 3/2. And again, that's where I'm getting that 1.5, negative 3/2. So let's plot that point, 2.6 and negative 1.5 in my rectangular grid. 2.6 down 1.5 brings me to about there. And if you can imagine overlaying this rectangular grid on top of this polar grid, those points are going to be in the same location. And that should always be the case. Let me show you another quick example here where I'm going to give you a rectangular point and I want to convert it to polar form. So in this example, the values that I'm given are x and y, and what I want to obtain in the end are r and theta. So what does r equal in terms of x and y? R equals the square root of x squared plus y squared. And what does theta equal in terms of x and y? Well, theta equals the inverse tangent of y over x. So if I take these basic equations and I plug the x and y that I have into them, I'm going to get that r equals 2 squared plus negative 2 squared. And that will be 4 plus 4, so the square root of 8, or 2 root 2. And then for theta, I'm going to be doing the inverse tangent of negative 2 over 2, which means that theta equals the inverse tangent of negative 1. So what you want to think about is, where on your unit circle is the tangent going to be negative 1? Well, it has to occur when the sine and the cosine value are equal, so that the ratio of them is 1. But it also has to occur where their signs are opposite. So if I just pull back my polar coordinates, it's kind of my polar grid. It's a good representation of the unit circle. So think about where my sine and my cosine values are the same. They're going to be the same at pi over 4 and multiples of pi over 4. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi, whoops. I did not draw those lines very nicely. It should actually be this one right here, and not this one. And then over here it should actually be this one, and not this one. Sorry about that, need to a little more carefully. Anyway, the idea is in those spots the sine and the cosine values are equal. However, in the first quadrant the signs are the same, second quadrant signs are different, third quadrant signs are the same, fourth quadrant signs are different. So we either need the angle in the second quadrant or the fourth quadrant to represent the inverse tangent of pi over 4. And if you think about what the range of inverse tangent is, it goes from negative pi over 2 to pi over 2. So your only options are these two quadrants. And so it has to be this angle down here. Since we can't go all the way around because we'll go outside the range, we have to go in reverse, and that'll be the angle negative pi over 4. So my resulting point is 2 square root 2, comma, negative pi over 4. So you should be really comfortable with going back and forth between points in polar form and rectangular form, as well as plotting polar points on a polar grid. Let's continue on and talk about converting equations. Or just in general, graphing polar equations. So there are many types of polar equations. You can get lines. You can get different types of circles. Different types meaning different radius lengths, different orientations on the polar grid. You can get something called a cardioid, which sort of looks like this, like an apple or a heart or something like that. You can get something called a limaçon. You can get different loops or flower petals, things that look like flower petals. So some of these names are really official, and some of them are much more loose. But anyway, the point is that with polar equations, you have all sorts of different shapes that you can obtain. So we're going to be looking at two methods to graph polar equations. One of those methods is by using some algebra and converting it to rectangular form. Oops, rectangular, missed my U in there. Rectangular form and graphing that way. Another method is going to be plotting points. And then, of course, you have your graphing calculator, which can help you as well. So I'll go into some detail about converting to rectangular form, plotting points, and using your graphing calculator to graph polar equations in my next video.